In this video, we walk through the process of designing and building a typical industrial control panel. We'll start by identifying what the machine will do, then draw a block diagram of the components and how they'll interconnect. Next, we'll pick the part numbers, draw the schematics, and design the panel layout. Finally, we'll assemble, wire, and test the completed system. This panel will be a remote I/O installation, and the controls are going to be used to run a flying cutoff machine. We'll be using a PS-AMC4 with a P1-RX for communication back to the primary controller and 4 Sure Servo 2 drives. We're also going to highlight some of the other components Automation Direct offers that can make your job easier, like Rhino Pro DC power supplies, Wago electronic circuit breakers, and rear safety controllers. The PS-AMC4 will control 4 Sure Servo 2 drives, and the P1-RX will let us control it all from an existing productivity PLC. The Rhino Pro power supply will power our control system, and the Wago electronic circuit breaker will distribute and protect our DC power. Now that the machine's purpose has been defined and the components selected, we'll draw our block diagram. If you've heard of a one-line drawing, you'll be familiar with the concept here. We just want to document the relationship between all the parts we're using, from power supply through circuit breakers to the components they power and to the sensors or motors they control. At this point, it's not important to know the manufacturer or model number of the parts you're using, but for the example, we already do. Note that we're not even looking for pin numbers or individual wires currently, just the relationships between components. It's time to discuss schematics. These are the drawings you'll use to wire components together. It's important to have a plan and stick to it. While there's no wrong way to organize your schematics, some localities or customers may require a particular style or method. IEC and NFPA styles communicate the same information in slightly different ways. Choosing one style over another is outside the scope of this video. For this example, we're choosing a hybrid approach where our pages are grouped by function and our wires are identified by potential, page, and line. We've chosen to identify all wiring that carries unswitched and AC power with a formula built like this. The first part is the voltage potential. The second part is a combination of the page number, the line number, and the column ID where the wire originates. This way, if someone is troubleshooting the machine, they can look at any wire and know where in the schematic to look. Point-to-point connections are described by the schematics. This goes farther than the block diagram by describing where every wire lands. If you don't have specific model numbers chosen yet, your descriptions will still be generic. For example, the AC input to a power supply will be labeled L, N, and G and D, where a manufacturer may assign pin numbers to these connection points instead. The last steps in the schematic package go hand in hand, choosing your specific parts or bill of materials and designing the physical layout of the control panel. In an ideal world, you'd be able to fully design your schematic, pick your parts, design your layout, and then choose a cabinet and sub-panel that has room to spare. But reality can get in the way. Often, you'll be giving a space to put a cabinet, and you'll have to do your best to fit everything inside while keeping thermal considerations and voltage separation in mind. With that said, we've chosen this layout with a few things in mind. 3-phase power comes in on the right, into the main disconnect, and back into the AC circuit breakers in the top row. The right side was chosen for the main disconnect since this cabinet has a cable-driven handle that mounts on the right side. The servo drive gets the bottom row for 2 reasons. First, this allows heat to rise away from the servo drives, and second, if we bring the servo cables in from the bottom of the cabinet, we don't have to worry about voltage separation for the servos. 24-volt DC power and signals stay to the left. Areas where 3-phase power and low-voltage DC power have to get close to each other are separated by wire duct dividers. Ethernet cables get their own bundle, but can share space in the wire duct with 24-volt wiring. Keeping with the theme of a bottom exit for cables, the PLC's I/O terminal blocks are placed at the bottom left of the panel. Additionally, components are spaced away from wire duct and other devices based on their installation manuals. This is done so these parts don't overheat under heavy load. Now that the decision where everything goes on our control panel has been made, it's time to mark the lines and plan the holes. Using a T-square and a mechanical pencil, measure and mark the lines where the DIN rail and wire duct will be installed. The square helps keep the line straight, and the mechanical pencil will draw a clear line so that it's easy to erase later. Mark the mounting holes through the wire duct and DIN rail, as well as any components that mount directly to the sub-panel. When marking DIN rail mounting holes, give them a unique mark to help you know which holes to bond for grounding. Before beginning, PPE or safety glasses are important. Use a center punch to mark a divot in the center of each hole marked. Then, using a number 40 or 3/32 drill bit, drill pilot holes. Cutting oil helps keep the drill bit cool and sharp. Using an 8/32 drill tap bit and plenty of cutting oil, cut threads in every pilot hole that will be used to attach wire duct and DIN rail. Other components like VFDs and disconnects may require different screw threads. Once all holes are drilled and tapped, deburr every hole on both the front and the back of the sub-panel. Deburring every hole will keep your screws aligned during installation and protect your hands from cuts and scrapes. Now that all of your holes are drilled, tapped, and deburred, use a bonding brush to remove any paint around the holes that will be used to attach DIN rail, as well as any non-DIN components that require a case ground. Carefully wipe off any metal shavings from the panel, then use WD-40 to remove any remaining pencil marks, and finally use isopropyl alcohol to clear any remaining residue and allow the panel to air dry. Now it's time to start adding parts to the panel. Start with wire duct and carefully align the segments with precise right angles using 8/32 panhead screws. Do the same with the DIN rail sections. Time spent here making the angles precise will pay off later in the build and will improve the final appearance, maintaining a professional look. When everything is properly aligned, tighten the screws firmly, especially the screws on DIN rail, since they're being used to bond the DIN rail to the sub-panel. Starting with DIN rail end blocks, attach all components to the panel based on the layout design. Keep components tight against end blocks to help them stay in place during and after the build. When installing terminal blocks, take advantage of jumpers or bridges available for the parts being used. They can save a ton of time by eliminating handmade jumpers. As components are installed, you may find that some fingers on your wire duct will get in the way of larger wires or cables. Luckily, wire duct is designed to accommodate this. Simply remove the cover of the wire duct and bend the fingers away from the center of the duct. They're scored from the factory and will cleanly snap free. Be careful with this though. Once a duct finger has been removed, it's off for good. Using the schematic package as a reference, apply labels identifying the components and terminal strips. Applying labels on the sub-panel is preferred, but for terminal strips or PLCs with wiring that runs above and below the device, wiring may get in the way of the label. In this case, applying the label to the duct cover is acceptable. Just be aware that years down the road, that cover may go missing. For terminal strips, use marking tags to label each terminal. Now it's time to start wiring the panel. The order doesn't really matter, but having a system for yourself is a great way to ensure nothing is missed. For this build, we're starting at the first page and working our way to the last. If it makes more sense for you to wire your I/O before your power distribution, there's nothing wrong with that. Be sure to mark the connections and pages as you go so you don't risk duplicating or skipping work. When wiring, crimping ferrules on the ends of your wires will keep stranded wire from fraying, reducing the likelihood of a short or bridge, making it easier to install wires in terminal blocks. Route wires carefully so higher voltages stay away from lower voltages. For example, on this panel, we've routed the 3-phase power up the right side duct through the main disconnect and back around to the AC circuit breaker bus lugs. Then the AC power wires run out of the bottom of the breakers and back down the right side of the panel to the 4 servo drives. The power feed to our DC power supply is the only higher voltage run that goes to the left, and since it must live in the same section of wire duct as some lower voltage wiring, a section of duct separator is installed. If there are locations where high and low voltage wires need to cross, be sure they cross at a right angle. This will reduce inductive coupling, which can introduce noise or signal fluctuations on wires nearby. Also, make sure that any wires that share the same duct are all rated for the highest voltage that will be present. As you cut, strip, and crimp the wires, be sure to label them to match the schematics. Multi-core cables should be labeled differently to identify that they are distinct from single wires. Labeling individual conductors with a multi-core cable isn't necessary unless the cores are landing far away from the labeled end of the cable's jacket. Once the wiring is complete, it's time to test it. Be aware that panel build may involve higher voltages that can be dangerous, so wear safety glasses and other required PPE safety gear and follow all local laws and codes to ensure your safety. Start by attaching the power supply and ground. Do not skip your ground, particularly during testing. The ground wire is there to protect you and the wiring by providing a safe path for errant power away from the panel. If you don't install a safe return path, you may become the return path. Use a multimeter to verify the incoming voltage is what is expected. Next, turn on the circuit breakers one at a time, making sure the expected device turns on with each one. Once each AC device is tested, turn off unneeded devices to limit the risk of shock or arcing. Leave the DC power supply powered on and move to your DC circuit protection. In this panel, we've used an electronic circuit breaker for all the DC components, but of course, electromechanical circuit breakers or fuses would be acceptable. Turn on the DC components one at a time, making sure the expected device turns on and that nothing powers up unexpectedly. Check for power where you expect it. For example, the power rail of I/O terminal blocks or the input side of a safety relay. Leave all your DC components powered for the remainder of testing. If everything checks out, it's time to move to I/O testing. Connect to the PLC and configure it with the I/O installed. Use a jumper wire to apply power or common if your inputs are sourcing to each input terminal block, making sure the correct input is activated in the PLC. Next, use the PLC's programming software to enable each discrete output one at a time and verify the selected output turns on and off as expected. Verify this at the expected terminal block. Some discrete inputs and outputs may require activation of the safety system if equipped. If this is the case, connect the appropriate safety inputs, activate the system normally, and continue with the testing. To test analog inputs, use a current or voltage simulator and verify the PLC is indicating the expected value. If you don't have a simulator, you can use an analog device of the same signal type and wire it to each terminal one at a time. To test analog outputs, use the PLC programming software to set the output value to a unique level for each channel and use a multimeter in the appropriate mode to verify the expected readings at the terminal block. If any channel doesn't operate as expected, make sure the I/O card has input power and the wiring is correct. Lastly, it's time to load the final PLC program if it's ready. Use the programming software to open the file and transfer it to the PLC. Depending on the application and program, you may be able to perform a full function check at this time, or this may be where testing ends until the panel is installed on the machine. Thanks for watching, and we hope that our video was informative.